צהריים טובים וברוכים הבאים. בדרך כלל אנחנו קבוצה קטנה בסמינר המחקר של מרכז צ'ייס ושוהם, אבל היום לרגל האורחת שלנו אני מניח שהרבה מכם זאת הסיבה לקבוצה הגדולה שהגיעה לכאן. שנית, התנצלות, אני קצת נבוך כי הכנתי את ההצגה של ברברה טברסקי, האורחת שלנו היום, באנגלית, אבל בשעה האחרונה הסתבר שהיא דוברת עברית יותר שוטפת ממני. היא שאלה אותי, כששוחחנו לפני בהתכתבויות אימייל, לפני שהיא הגיעה לארץ, שאלה אותי אם היא יכולה לדבר, אם היא צריכה לדבר בעברית. אמרתי לה, דברי בשפה שנוח לך. אז לאט לאט מסתבר לי שכנראה נוח לה עם עברית לא פחות מאשר עם אנגלית. היא עדיין תרצה באנגלית, אבל לפחות כל ההתנצלות הזו נועדה לומר למה אני אציג אותה באנגלית. כי זה מה שהכנתי, עכשיו אני צריך לתרגם את זה. אוקיי. פרופסור טברסקי הגיע לכאן במסגרת הארגונים וההרצאות שאנחנו מגישים, נותנים סביב כנס צ'ייס, כנס המחקרים השנתי של מרכז צ'ייס. היא תיתן פה בארץ עכשיו 3 הרצאות, היום ההרצאה הראשונה שלה, מחר היא תיתן הרצאה נוספת שתעסוק בג'סטרס, מחוות, במסגרת הקולוקביום של המחלקה לחינוך ופסיכולוגיה כאן. באיזושהי הרצאה אני לא זוכר. אתם זוכרים עליי? מה? 2:30? מה? 11. ההרצאה תעסוק בג'סטרס, מחוות, נושא שונה מההרצאה של היום, ואת הרצאת המפתח שלה בכנס צ'ייס היא תיתן ביום רביעי בפתיחה של הכנס. פרופסור ברברה טברסקי, ההצגה שלה תהיה קצת שונה כי היא קשורה איפשהו לרקע הישראלי שלה, כמו שאמרה לי, בעצם מין ישראלית בגולה. She studied cognitive psychology at the University of Michigan. In graduate school, she met the dazzling young Israeli Amos Tversky. They married, moved to Israel, and she taught at the Hebrew University for a number of years. After going to Stanford on a sabbatical, they ended up, like lots of Israelis, staying up there in the US. Professor Tversky recently took an early retirement at Stanford, though she still has research projects there, and took a position at the Columbia University Teachers College in New York. Her research is focused on memory, categorization, spatial thinking, and language, and event perception and cognition, with applications to computer science, design, linguistics, geography, education, and more. רשימת הפרסומים שלה is very long on these topics, and I'm not going to elaborate on these. Today, Barbara will talk to us, and she will explain the slight deviation from the original title. She will talk to us on cognitive design principles, and the stage is yours, Barbara.
תודה רבה יורם ותודה לכולם, תודה לאוניברסיטה הפתוחה על ההזדמנות להיות בארץ. מאוד נעים להיות כאן ולראות קהל של חברים שלא ראיתי שנים. יורם ביקש שאני אסביר את הכותרת. אני אדבר, הרצאה היום היא הרצאה קטנה ומצומצמת. ההרצאה ביום רביעי תהיה רחבה על בכלל איך גרפיקות, דיאגרמס וכן הלאה, communicate. וההרצאה היום זה איך מוצאים עקרונות להפיץ דיאגרמס בתחומים מאוד מצומצמים. ואני אעבור באיזשהו שלב לאנגלית, כי אני לא יודעת את כל המונחים בעברית, מזמן לא הרציתי בעברית. אוקיי, אבל אם יש, אני מוכנה לקבל שאלות גם בזמן ההרצאה, אז אם יש, יש לי בעיות שמיעה, אבל אין לי בעיות להבין עברית, אוקיי? שמיעה יש לי. אוקיי, when the mind runs out of space, which it often does because our working memory has a very small capacity, so when the mind runs out of space, it uses the outside world. It makes trail markers so that you can remember the route, and there are trail markers all over the world. I remember when I went to grade school in a small town outside of Chicago, I went through a park where Indians had lived many, many years before, and there were trail markers along the way to my grade school that they had left 150 years earlier. So trail markers to mark the way, notches on sticks and bones to indicate how many sheep you have, the pile of stuff that you leave by the door so that you remember to take it to work in the morning, and most of all, paper we used when the mind runs out of space. And without that, it would be very difficult. This is something that human beings, that I think is unique to human beings. Other animals make tools to increase their physical well-being. Monkeys use ants to get, use sticks to get ants out of logs and things like that. But I think only human beings use the outside world and make tools to increase their mental well-being and their mental capacity. So I'm going to call these things external representations, diagrams, graphics. I'll use those words more or less interchangeably, and they're all cognitive tools to increase the capacity of the mind. One thing that they do is they increase memory. They augment memory so that you can remember more than the 7 plus or minus 2, even that's probably too many, things that you can keep in your short-term memory. They also augment information processing. So imagine doing multiplication or taking square roots without having a piece of paper. You run out of mental capacity. But external representations do more than that. They use space to represent both literal space, as in a map, and metaphoric space, as in a diagram, and action as well. They promote inference and discovery. They allow creation and revision and inference by a community because they're public. They're a way of making my ideas public so that you can see them and comment on them. And again, I think they're uniquely human. So I will talk very little today about these sorts of things, but my talk on Wednesday will go into these issues in much more detail, on how, especially on using space to represent literal and metaphoric space in action, and promoting inference and discovery. So we can distinguish two kinds of graphics. There are visualizations of things that are inherently visualizable, like maps. The paradigmatic case would be maps, and they're found in cultures all over the world, not necessarily on paper. They're ancient, and they seem to be pretty universal. Then there are visualizations of things that are metaphorically visual, like graphs, charts, and diagrams. And for reasons that aren't completely clear, these are recent inventions. They were invented in about the late 18th century in Switzerland, in England, and there are few scattered examples that are older, but not many. If some of you have examples of old visualizations of metaphoric things, I'd be really eager to see them. So they're modern, and that's a bit of a mystery. So here are some of the kinds of maps. This is the oldest map known. It's 6,000 years old, and it's on clay, which is one of the reasons it survived. I'm locked in here by the microphone, but I'll move aside for just a second, maybe. Well, okay, I'm not going to do it. You can see, if you look carefully on that map, you can see that it's very schematic. It's showing roads as lines. It's showing more than one perspective, and the next one will show you that even more. This is also a petroglyph. It's only 4,000 years old, but it's not the petroglyph itself. It's the drawing from the petroglyph. And you can see very clearly there that lines are represented as, that roads are represented as lines and houses as these boxes, and that it's actually showing you two perspectives at once. Okay, it's giving you an overview of the road system and a frontal view of the buildings, which is a very useful sort of thing, but it is mixing perspectives. It's done artfully so people can understand it. So another kind of map. These are maps, these are pieces of wood. They're carved wood, they're very beautiful. They were used by coastal Indians in Greenland, Eskimos, to navigate along the coast. And they reflect the curvature of the coast. And if they fall out of the boat, they float. And they're reversible, so you can use them from both sides, okay? And I'll show these again. This part of the lecture is similar to what will be on Wednesday. Another example of navigators' maps are these shell and bamboo stick maps. They were used by South Sea Islanders to go thousands of miles in the open ocean where you can't see from island to island. The islands are the shells. And the bamboo sticks are the ocean currents, which you can think of as the highways of the ocean. And they were useful enough that many of the navigators got back home, right? I'm not sure if all of them, but many of them. Okay, this is another kind of map. It's shown on a hand. This was used by Northwest Indians in the United States and Canada to show the cities, where the cities are. You can see Halifax, Boston, New York, Montreal, Quebec. And when people would ask where you live or where are the cities, they would hold up their hand and point on their hand where they were. So you carry a map in your hand, just like you carry a calculator on your fingers. Okay. So what about diagrams? There are old diagrams. They're very realistic. So these you can find if you visited Egypt and gone into the tombs in Luxor, something that שאני ממליצה מאוד. You can see diagrams of how to make bread, from sowing the wheat to actually making the bread, step by step. Trajan's column shows the events of the wars. Emperors are fond of this. We're showing all the wars they win. The Bayeux Tapestry, another military invasion. Okay, so you've seen many examples. These are older ones and not newer ones. So again, some of the ways that I'm repeating, some of the ways that external representations augment cognition is to record information, as Trajan did, convey information, and that'll be our focus today, promote inferences, enable new ideas, facilitate collaboration. So one of the first things to notice about good graphics is that they schematize. They don't show you everything. They only select the information that's relevant. So they're not realistic. They take away information that's irrelevant, and they emphasize, simplify, and even distort the relevant. So if you wanted to find your way around Kyoto, this aerial shot of Kyoto would be a very bad map. It's very realistic. It shows you all that you can see about Kyoto, but it doesn't give you the detail that you need. It even shows you the road structure, but it's so cluttered by everything else that it makes a very bad road map. So one of the hallmarks of good design is the London tube map, and it does schematize. It turns all the tube lines into horizontal and vertical and diagonal lines, so it's not true to reality. Distances aren't right, so it's distorting distances. However, it gives you very clearly all the tube stops and all the connections between tube stops, which is the information you need. So it's a good schematization, and it's become a model of design throughout the world. So good graphics schematize, as we said, they include essential information and omit the irrelevant, distracting information. Good graphics are often developed from informal user testing over the years. So something like a route map is something that we've probably been using for millennia, ever since people were people and somebody had to tell somebody else where to find the good berries. They probably scratched a map in the sand with the landmarks so that you could get there. So that the principles of making route maps are something that we all grow up with. And if I draw you a map and it's not clear to you, then you'll ask me, right? And then I'll clarify it. So it grows up, these things develop from you and me trying to negotiate them until we fine-tune what they should look like. And by now, we have all kinds of ways of fine-tuning them. We know the vocabulary, how to do it. In many of the same ways, spoken language developed, right? Through discourse, people speaking to each other and getting fine-tuned. And that leads to a process of many words getting shortened. Useful words get shortened. Not so useful words stay long. But it's, again, a kind of user testing. We use it for comprehension, production over and over again, and it gets better. So this kind of user testing happens to good graphics and good schematizations, but many of them haven't had that time to develop. So we've developed a procedure for bringing that process into the laboratory and short-circuiting the hundreds of years that it takes to make it good. And that's what I'll tell you about today, using 2 examples. Okay, so good graphics schematize, but there are so many bad ones. Okay, here are some bad ones. Here's another bad one. And, you know, these are graphically very beautiful, but they're just too complicated, too many parts. How can you see them all? These aren't even the worst, right? You have them in science too. So this looks like a very beautiful example of the rock cycle. But if you look at it closely, which you probably can't because you can't read it, from a distance it looks great. Those arrows are ambiguous. Arrows have lots of meanings. I'll talk about that a little bit on Wednesday. But one meaning is the next step in a process. Another meaning is movement. Things move from one place to another. Another is that they change state. I mean, there are lots of meanings to arrows. There are arrows all over the place here, and some of them are even marked. But you can't understand which is which. Is it things that are moving? Is it changes? Is it the next step? And so forth. So I've showed this to geologists. Yoram, maybe you can comment. Then I have a whole collection of them. You can get them off the internet, thanks to Google Images. And they just aren't clear. They're very beautiful, but they aren't clear.
There is a question here, whether there are some. You said you collect.
Yeah, I'm happy to have questions.
There are sometimes, for the sake of simplification, we create misconceptions, such as the solar system is a nice example. You show something which is a complete misconception of the orbit, and it's the opposite to what.
Right. So the question here was about misconceptions, and the London subway map is again an example that if you schematize so that the information is very clear and very simple, this can create misconceptions. So distances here aren't real. And in fact, you can be quite confused by this and actually change subway lines when all you would have to do is walk a block, right? And you've waited for another tube and you've wasted all that time when all you'd have to do is walk a block. So that sometimes in the interest of simplification, in the interest of what we have to communicate this moment, we distort distances. I can say, though, that I once had to use this as a walking map because I had to get out way east in London, and I went off my walking map, but it was still on the tube map. And I got there. And I got there on time, right? And everybody I asked in the street sent me the wrong way. So I wouldn't recommend it as a walking map, but it worked for me once. But yes, many of our schematizations simplify. Language simplifies, right? We have lots and lots of subtle concepts, and words are brutal for expressing them in many cases. But these are the only tools we have. And we know that we have to simplify things in order to teach them. So yes, thank you. We can create misconceptions, and that's a worry. That's the downside. Okay, so can we improve on these sorts of diagrams? I think so. So we've developed a couple of principles for designing effective visualizations in any field. One principle is a principle of congruity, which you could translate hatama. And it all sounds big and fancy, but it's really quite simple. The content and the structure of the visualization of the graphic of the diagram should reflect the content and structure of the desired mental representation. So these diagrams, in effect, do that. They show you the structure of the car and where the clock is quite clearly. Or they show you the structure here of the air filter and the machine that it goes into quite clearly. So the structure is quite there. It's all there. So in some sense, the diagram is a good mapping. It's mapping accurately the structure of the actual physical object to the diagram. So that's what we mean by congruity. However, the problem with these diagrams is the second principle, and that's the principle of apprehension, which is tvisa. It's that something has to be easily perceivable. And these aren't easily perceivable, right? They take an enormous amount of work to perceive. There's too much going on, too much detail, and it's too small. So the second principle, and sometimes they're in conflict, as you can see here, is the principle of apprehension, and that's that the content and the structure has to be readily and accurately perceived. Okay? And when there's too much information, we know that people can't perceive it. So are those principles more or less clear? Because I'm happy to answer questions. Okay, so our research program, and this is a program that was developed with all of those authors at the beginning. They're an interesting collection. Pat Hanrahan is a computer scientist who's done who's won 2 Academy Awards for the graphics that he's done, technical Academy Awards, for making the hair on every hair on people's head look realistic. And then he went into visualizations that are more schematic and less realistic, and we got together. We got together partly through a student of his, Manish Agrawala, and Chris Stolte, who did the work on an algorithm for route maps that I'll talk about. We also added Julie Heiser, and Paul Lee, by the way, did some of that work as well, the psychological work. And then we added Julie Heiser and Marie-Paul Daniel, who was a postdoc from Paris, to do the work on the assembly diagrams. So it's a big group of people that have worked together, some computer scientists specializing in graphics, and some cognitive psychologists. So what we've tried to do is uncover the mental representations that people have. Yes, question. So the question was, will I talk about video clips, animations? And I will talk about animations, but not too much today, maybe more on Wednesday, and more at the end if we have time. But I will get to that in a minute. So the research program first undercovers the mental representations, because it's the mental representations that we want to convey, okay? Then, and we have a research program that reveals how these mental representations are expressed graphically in diagrams, verbally in descriptions, and manually in gestures. So, and all 3 of these will converge to show the same underlying syntax, and, well, not quite syntax, but semantics, and that'll give a clue to the mental representations. So this is for the cognitive psychologist. Then from that, we create cognitive design principles. We extract what is the essence of the mental representations, and we want to apply those to the diagrams. And then the computer scientists take over, and they make algorithms using these design principles to create the diagrams. So I think that last step you don't necessarily need. You could deal with a graphic designer, but in our case, we were interested in cases where you want lots of diagrams in a minute, and then you need computer scientists. So our 2 examples are very common everyday life examples. They're things that we all need to do in everyday life. One is route maps. The other is put something together. So think IKEA, which I know has gotten here, knock down furniture that you have to put together, or how to work a Xerox machine or your cell phone or whatever. These are things, again, that we need to do all the time. So we deliberately picked real-life examples, although we're now trying to apply this to science diagrams. Okay, so route maps. We first did studies on the cognitive psychology of route maps. This was work with Paul Lee, and he caught hungry students outside the dormitory, and he asked them, do you know how to get to a nearby Taco Bell, a nearby fast food restaurant? And if they knew, we gave them a piece of paper, and half of them we asked to draw a sketch map, and half of them we asked to give verbal instructions. So the sketch maps looked more or less like this. They're the kind of sketch maps that any of us would draw. Here's another one. And these contain the shortcuts and distortions that actually are distortions of memory. So we've also done research in memory for environments, and they make the same kinds of errors. So one thing, all turns are summarized as right angles. So even though maps could be analog and they could show the exact turn angle, people tend to make turns at right angles. The other thing you'll notice about this is that the roads tend to either be straight or curved. And again, maps are analog. They could show the roads exactly as they look. They don't. They tend to make this dichotomous distinction, either straight or curved. The third thing to notice about these maps is that the distances are distorted. Now, you don't know this environment, so you don't know that, but that distance here from the intersection of Palm Drive and El Camino to Taco Bell is that distance from the corner of Palm Drive and El Camino to Taco Bell is bigger than the whole map, okay? But you don't have to make any turns there, so it doesn't matter, right? So that you can understand that. So you see already the maps are schematized and distorting the information in exactly the ways that the human mind distorts the information. When there's a lot going on in a small area, it gets expanded. When there isn't a lot, no turns, in a large area, it gets shrunk. Okay. The directions look similar. So we got a lot of directions with bullet points, and this was before PowerPoint. So you can't blame PowerPoint. Anyway, I think bullet points are good. They're a clear way of thinking. So you got very crisp descriptions like this, just a series of right and left turns. We also got descriptions like this, and this is only a third of it, okay? So this is someone trying to be helpful, but it's maybe too helpful, right? But what we did then is we looked to see, is there the same underlying mental model driving both the descriptions and the depictions? And we found yes, that the same underlying mental model drives both. On this we relied on some work from a French colleague, Michel Denis, who had collected many, many descriptions of his university outside Paris, and then he got a grant to go and study route directions in Venice. Okay? This is a deal, right? Okay. So in Venice, as you know, is terribly confusing. So you can look and see that the same elements appear both visually and verbally, and I've drawn them up there. There are turns, and they're summarized as pluses or T's or L's, and they're usually summarized as right angles, whatever they are. In English, you say, make a right, take a right, turn right. In Hebrew, it's similar. You don't say how many degrees you're turning. Then you have straight roads and curved roads. For straight roads, you say go down. For curved roads, you say follow around. Then there are landmarks, and they're usually indicated by blobby things like squares or circles, or the names of the streets, and about half the people give arrows. The arrows aren't necessary. So we thought, well, what we have here is a toolkit for verbal descriptions and a toolkit for visual descriptions, and we gave people the toolkit and then a whole bunch of, from here to there, the directions that we asked them to write, and we said, if the toolkit's not enough, then add. And as I said, they got either all those verbal symbols or the visual ones, and almost none of them added. In other words, the toolkits were pretty much sufficient. Okay, and we thought this could be used for automatic translation. You could automatically translate from a visual representation to a verbal one. We thought the computer scientists would pick up on that. They picked up on something different, and they're smarter than we are. They knew how to make this, turn this into money, okay? I didn't. And it was these two graduate students. So here are the design principles for route maps. The exact distances aren't important. The exact turn angle isn't important. What's important are the paths, the nodes or the landmarks, and the turns. Which way to turn when you get there, okay? And you might ask, if this is only the information that's important, and it's not sufficient information and it's distorted and wrong, how come we get where we get, okay? And the answer to that is that we use maps in an environment. And the environment disambiguates. It tells us what's correct and what's not correct. So if I think that a turn is 90 degrees, and it actually turns out to be 120, right? I'm not going to go 90 degrees, right? I'm going to turn the way the road goes. So I don't have to know the exact turning angle, because when I get to the intersection, I'm going to go the way the road goes. Similarly, if I think it's 5 kilometers and it turns out to be 3 or 7, I'm not going to be stubborn about that. I'm going to go until I get to the next landmark. In other words, it's giving insufficient information, distorted information, but because it's used in a context, you won't go wrong, okay? You might, but, I mean, I would, but you're less likely to go wrong. And the point is that any graphic, any visualization, any verbal instruction is always used in a context where there's some agreement as to what is the surroundings, right? That's filling in the information that isn't in the words or the graphic. Okay, so this is what our computer scientists did. They were very clever. That's Manish Agrawala and Chris Stolte. On the left are the maps that you usually get in the United States when you download a route. Okay? Those maps are terrible. They don't tell you how to get on and off the freeway, which is the only tricky part, right? And they're filled with all kinds of clutter that you don't need. So what they did is they developed an algorithm, and their sort of maps are on the right. They developed an algorithm that quickly computes. This algorithm can do it for many thousands per second or per minute. In other words, it doesn't stop. It keeps up with the demand. They developed an algorithm that draws you a route map along the principles that we described earlier in no time. And in beta testing, 96% of the users raved about it and thought this was a much better map. And you can find it now, at least, they sold it to Microsoft, and you can find it at mappoint.com. You have to ask for a line drive map, and then you get something like that. Okay, any questions at this point on route maps? Yeah, back there. Sure. I mean, the question is about terminology. Why didn't I use the word abstraction instead of schematization? I could have. Abstraction, it's used a little bit more than I would like. So schematization kept it at the level of maybe a schema, a drawing, a sketch. So that was why. But people are puzzled by the term schematization and abstraction too. But sure, it's abstracting away the information you need. Sure, you're right. And what if you're in the Sahara, right? I mean, sure, and where there are no landmarks. How would these sorts of maps apply? And it's extremely difficult. In those environments, we made sure people knew the environments. In environments where you don't know landmarks and paths, it's a problem. You can't give directions, period. So I had a student once who was an Eskimo, and her grandmother was a river navigator in Alaska. And in the winter, the river it's tundra, it's all frozen. And even the river is completely frozen, or almost frozen. And she gets around with landmarks and paths. So it still is, there's some sort of implicit path that they know, and there are landmarks that are trees or wells or whatever. And they're still doing that same kind of navigation. I don't know how else you could do it.
But you can still draw a map with direct or straight 90 degrees.
Right. So I'll give you another example. There's a lovely set of books that are published by the University of Wisconsin. There are about 8 volumes now that collect maps all over the world. You probably know about it. It's Woodward and somebody else. The editors keep changing. And one of them is on maps from emerging societies. So these are societies that don't have written languages, for example. So if somebody went to New Guinea, where, again, navigation is on the river, took people who had never been to school in their lives, never seen paper in their lives, certainly never seen a map, and these are river navigators, and asked them to draw maps. So they go from development along the river. What they drew are straight lines. So they schematized the river as being straight, even though the river wasn't straight. And all the settlements along the river were schematized as circles. So it was like pearls on a string. So again, the way they conceived of it conceptually was as landmarks on a string, landmarks and paths, right? And this kind of abstraction, that's how we conceive of the network, right? You could diagram languages as nodes and paths. I mean, this is something very basic, I think, about human thought, is that you can think about verbs are predicates on objects, right? We have objects that are stationary sorts of things, and things that lead from object to object, or settlement to settlement. So I think this idea of paths and landmarks, even though it grew out of geography, really captures something very basic about human thought. How to get from here to there. Okay. Okay, other. Sure. So the question is expertise and talent. And these things trade off, ability and talent. And both things are absolutely factors. And people often, if they're drawing a sketch map for somebody else, assess the expertise. Right? They say, what do you know? Right? And they pick it up very quickly, and they draw a different kind of map or give different kinds of instructions. For someone who's an expert, you can say that it's. I mean, when I first moved to Jerusalem, I had to learn landmarks that hadn't been there. Eged Yashan, right? I mean, Eged Yashan. Princess Mary Street. That was Shlom Tzion Malka. That was the name of the street, but in the Tkufat Mandat, Princess Mary. So I had to learn Princess Mary. So expertise does make a difference, how much somebody knows, but we're fairly good at assessing that. Again, this isn't error-free, right?
The other issue is shortening the path. What I mean is, if somebody is familiar with, let's say, 3/4 of the path, then for them, they will just ignore that
right.
piece and will just concentrate on the quarter that they're missing.
Absolutely. Absolutely. They'll say, you know how to get to X, and then from there it's this. Right. No, absolutely. That would be another thing that people would do. Right. So another thing that's missing from these maps that needs to be there is what happens when you overshoot. Right? There is no error correction there. And we all know that we overshoot. So how do I know when I've gone too far? And that's one of the big... So these aren't perfect. Any schematization isn't going to be perfect. There's going to be some error. But you can err on both sides. If you give too much information, then what you need isn't clear. If you give too little, then there's more room for error. So it's a trade-off like anything. Yeah, okay. Other... And ability, I'll get back to. So keep that question. Okay. So I'll come back a minute to I may come back to route maps, but then I may not. So I'm going to go now to assembly diagrams. The truth is that the work on the route maps we did not in parallel. We'd done the route map work, the psychology of it, and then the computer scientists came to us. But we had such a good time together that we decided, let's do another project. And we thought a long time for another project, and then we thought, how about furniture assembly? And at that point we thought, well, maybe IKEA will support our research. We couldn't get them interested. We tried steel case, whatever. It wasn't easy. Okay, so for assembly, you need a mental model of the system, and you need of the thing you're going to build. I should have said the object. You need a mental model of the object, how the parts fit together. You also need a mental model of the action that you need to put the thing together. So you need two mental models. And again, here's a bad one. This is one of the students brought home one of these barbecues. And that was her instructions for putting it together. And you always end up with extra parts, right? Why did they give you all these extra parts? You didn't need them, right? So, right. So we said, so we took something simpler. We bought TV cards. We went to Target. Yeah, question.
I'm sorry to trouble you, but for the barbecue, did you study anything about gender differences on that?
We don't get... Okay, we didn't study the barbecue. We did something simpler. We get no gender differences. None. So I should say that up front. On the cognitive map work, and I told you just one corner of our research on cognitive maps, no gender differences. Not even where you're supposed to get them, that men are supposedly better at cardinal directions, and women at landmarks. Everybody's bad at cardinal directions. Men and women, and we get no sex differences. Now, most of these experiments were run at Stanford, and they're bright students. But we get gender differences on the spatial ability measures, and I'll get to that in a second. We just don't get them on the tasks. And I think one reason is that all of these tasks can be done in more than one way. So you don't do it by one way, you do it by another way. And we're all adept at figuring out different ways to do it. I mean, if you figure out how we multiply, ask people how they multiply. Do they get to multiply to the nearest 10 above and subtract to the 10 below and add? I mean, how do you do fast multiplication? Everybody has a different system. So similarly with these tests, we can do them in more than one way, and we all have a lot of bag of tricks of how to do them. Okay, so this is our task. This is actually one of the research assistants. She's from LA. Northern Californians don't dress that way. What we did is we first gave people this TV card, and we bought a huge number of them at Target, and then realized Target was changing models. So we bought as many as we could, and then there were none left, and we needed more. So we wrote to the manufacturer to get more of these TV cards because they were getting broken. The students don't always put them together right. And it took them eight months to send it. These are Canadians. It took them 8 months. We have money. They have TV cards. They can't sell them. They're just sitting in a warehouse. We even offer to give them our instructions, which are better than theirs. And they aren't interested. It took them 8 months to send the TV cards. Now I have too many. So if anyone needs TV cards... Okay. So the students first learned to... They saw the TV card with the picture on the box, and they assembled it using the picture on the box. Okay? And they all could do it. It took them a while. After they'd assembled it, we asked them to produce instructions. And we did many different experiments. They produced instructions either by making diagrams, sometimes with words, sometimes without, or by only verbal instructions, or by gestures. And the gestures could be only gestures. They were told to make a video for people that didn't understand English, or they could use gestures and words. So we have, and I won't go into the details of the data and all of that, but we've tried all three because we think we can learn something from each of them. Okay. I'm going to talk mostly about the diagrams because that's the topic today. So this is one example of the diagrams that subjects drew us, participants drew us. These are very good ones. Okay, and I should point out they have a narrative structure. They're showing you the step-by-step, can I pull this out? No, I can't. So I'm going to repeat it. They show you the step-by-step assembly, but they also have a narrative structure. They have a beginning, middle, and end. So the beginning up at the top is a part menu. They tell you what parts are going to be used there. They give you step-by-step, and I'll say more about that in a minute. And then there's an ending. See the ending? They mark an ending. So these instructions they're narrative, right? They have a discourse structure so that they have a beginning, middle, and end. And our gestures get the same thing. They introduce the task, they go through step by step, and they have an ending. And the ending is usually something like that. You'll see some more endings. So this is a high spatial person. So those are good diagrams. This is an example of the verbal instructions. I'm not going to read through it because I won't say too much about it. And here are our gesture people. We also, in all of these studies, we looked at spatial ability. The tests that we picked, there are many tests of spatial ability. They don't always correlate. Okay? So that spatial ability, like verbal ability, is multifaceted. There are many aspects to it. The one spatial ability measure that seems to correlate the best with the most things is something called mental rotation. And this is one item from a test of mental rotation. You get this target figure, and you have to figure out which of these 4 target figures matches. Okay, would be the same one if you mentally rotated it. The alternatives are mirror images. So it's a very hard task, okay, and it takes time. And I don't know if, there are the answers. So this is a pretty bad reproduction, so it's hard to see, but these 2 with the X's in them are actually mental rotations or actual physical rotations of this one, so that if you rotated this to meet that, it would match, but these other 2 would be mirror images. So you get 20 of these, okay, and it's timed. And this task, men usually are better than women. However, if you get practice, everybody gets better and the difference gets smaller. If you take away the timing and don't put time pressure, there's almost no difference between men and women. But this particular spatial task, you do get differences for men and women. It's going to predict our performance, but we still don't get sex differences with men and women. In other words, it's a small effect. Other spatial ability measures don't necessarily show differences between men and women. This one does. So this is mental rotation. Again, 20 of them. 10 is usually the median, and our highs are above 10, our lows are below 10. Sometimes 9. This is on many different tests. Okay. Our high spatials put together the TV card faster. Okay? Remember that they're learning to put it together from the picture. So it's very much a spatial task. And it very much takes some sort of mental rotation to figure out from the picture what you should do with all these boards. So the time for the low spatials is 12.5 minutes. The time for the high spatials is 7 minutes. So it's a big difference. The high spatials are assembling it in half the time. They're also making fewer errors. This is errors not in the assembly. They're making fewer errors in the instructions. Okay? There was one very common error in the instructions, the common error that people made when they tried to assemble it and when they made the instructions, and the low spatials tended to make more of them. So 88% of the low spatials are making an error, and only 12% of the high spatials are making errors. So spatial ability does affect both the assembly and the accuracy of the instructions. It also affects the quality of the instructions. So here's another bit of instructions from a high spatial. These are with words, and some of them weren't. But again, you see they're step by step. They show the perspective. They show perspective, first of all. They show the perspective of assembly. They show you the right perspective that you need for assembly. They do a third thing. They use arrows and guidelines to tell you how parts attach or how you put in screws and nails. Okay? So those are 3 things or 4 things that the high spatials do that the others don't do that are critical here. It's step by step, showing perspective of action, and using these extra elements of arrows and guidelines. Okay, another high spatial. So they're sloppy, but they're giving you, then this one doesn't go through step by step enough. It skips steps, maybe because they're high spatial, they don't need it, but it is giving you perspective in some step by step. Here's low spatial, no perspective. And in fact, this is a really good low spatial. Okay, some of them didn't hardly drew diagrams, or they just gave you a part menu. Okay, so here's another low spatial. It's very hard to say. They were trying, but they just didn't get it. So here's our narrative structure again. This ending here with the sparkly lines, where'd my arrow go? I lost my arrow. But the ending there with the sparkly lines was the typical ending. They put sparkly lines. They have to tell you when you're done and feel good, right? Look at this lovely TD card. So we could distinguish diagrams that were structural, that just showed you the structure, or diagrams that were action, that showed you how to put it together. This is an action task, okay? So it turns out that our low spatials gave us, for the most part, structural drawings. Our high spatials didn't give us structural drawings. They gave us action drawings. And you can infer the action from the structure. You can't do vice versa. Okay, so if we go back to the structural diagrams, if you see the structure, you can't infer what actions you need to get to it. But if you see the action diagram, you can infer what are the actions that you need to do. Okay? So our low spatials gave us structural drawings, our high spatials gave us action drawings, and then we did ratings. We asked people, we took a whole bunch of these instructions, gave them to other people, gave them for rating, and it turns out that people prefer the instructions produced by the high spatials. This was a new set of subjects. They did the same thing. They put the TV card together, and then they rated instructions instead of writing their own. They were both high spatials and low spatials. Everybody likes the high spatial instructions. The low spatials like them too. Okay, was that your question? Sure. All of them had experience with this sort of thing. You can't live without it. But it's true that the more experience you have, the more high spatial you are, or more high mechanical. So those things do go together. As usual, expertise and ability trade off. You can increase your ability by becoming more expert, right? I'll never be a Mozart, right? But I could probably play the piano better if I practiced more, right? So that they trade off expertise and talent, right? And it's true that the more experienced people, for whatever reason, tend to be higher mechanical ability, higher spatial ability. Okay, but everybody, high spatial and low spatial, prefers the diagrams that the high spatials made, step-by-step perspective and action, and people perform better. We gave them these instructions. They perform better with these instructions. So, so diagrams convey the structure directly, and then they convey action with using arrows for movement and these guidelines for point attachment, for where you put in nails and screws. So language reinforces these principles. We also scored the language, and we scored the language into whether they were general statements like you're putting a TV cart together, or what a nice piece of furniture you have now, or temporal, first, second, third, fourth, or action, put this there, or insert this there. They were using verbs of action, or descriptions, the shiny side of the board goes up. And most of the instructional components were action, again, because they're describing action. And again, we found a difference. Our high spatials not only draw more action, they say more action. Okay, so our high spatials and these are different subjects, they're saying more action than the low spatials. So again, here are assembly design principles, step-by-step action and perspective. And these are they were inserted into this algorithm. Manish Agrawala, Dwantan Fan, a whole bunch of people worked on the algorithm. And it was presented at SIGGRAPH, which is a big honor for graduate students. And these are the instructions that the algorithm constructed. The algorithm begins with an object. It decomposes the object into parts, and it decides the order of the parts depending on the visibility in the diagram. So that the algorithm is constructing the diagram at the same time that it's constructing the order of assembly, so that it will be visible from the diagram. So this is the first time that an algorithm of this sort did both those things together. The algorithm does step by step. It shows the perspective of action. It uses arrows for actions. You can see there. I don't know why I've lost my arrow. Here it is. There. It uses arrows that are actions, and it uses the guidelines for where you put in screws and nails. Okay? And these are the wheels. What the algorithm does not do is turn this upside down, because you really need to do that. It's much easier to put the wheels in if it's upside down, and we debated for a long time. In other words, the cognitive principles weren't sufficient for making the diagrams. We had to think, too. And would it be harder to show the rotation of the diagram, or would it be easier to keep this always upright and let people infer that they're better off turning it upside down? And we made the call that it's better to keep it upright, that people think about the object as upright, but we didn't test that. That remains to be tested. So even when you develop these cognitive principles, there are still places where you have to guess, use an educated guess, or run another experiment, which we could have done. So their algorithm is very general. It also pulls apart Lego, and it gives you back the Lego instructions. And the Lego instructions are considered a gold standard, because they're used by children all over the world, and they have no language. Lego's easy, because there are all those blocks of different sizes, and they fit the same way. So Lego's pretty easy, but still it was nice when we got back the Lego instructions. It also does other pieces of furniture and gets back very nice instructions. So, and these design principles we think generalize. We've shown you, the example we've used is to show you how to put something together, but we think they would generalize to how something works. So if you had to explain how a carburetor works or how a Xerox machine works, that many of the same principles would apply, how the heart works. And as I said, we're applying this sort of research program to generating diagrams in science now. We're working with chemists and with meteorologists. Okay, animations. There was a question about animations. Yeah, another question first. So the question was, we have a mental model of action and a mental model of structure, and I didn't go more into that. So the mental model of structure would be the relationship of the parts to each other. And we would get that more or less from the prepositions that people were using or from their diagrams directly. The mental model of the action is actually the actions that the human being has to take to put it together. And that, again, we could get from the diagrams, the arrows, the guidelines, or also from the words. So I went into that more in the route maps and not as much in here, right? Okay, so animations. And I've been trying to get somebody to do the animated version of this. You know, it's easy enough to animate that algorithm that I showed you, those instructions. However, Julie Morrison and Mireille Betancourt, another French postdoc who worked in my lab for a couple of years, and Julie Morrison was a graduate student with me. We did a survey. This is 10 years ago, more than 10 years ago. We did a survey then of all the literature on using animated graphics and comparing them to static graphics for educational reasons, for teaching somebody how to work something. So we're not using animations like the fill bar when you're downloading a file, the fill bar that tells you what percent, and it keeps changing, right? It goes up and down and up, right? That fill bar. We're not using online animations that are keeping track of something. Only animations that are being used to explain how something works or how to do something. And we took animations where the same information was in the static graphics as in the animated graphics, because sometimes the animated graphics have more information. That's not fair, right? You can't learn information that isn't there. And we found no study where animated graphics were better than static. None. And we expected animations would be better because of congruity. Animations are showing change over time, And they're using change over time to show change over time. So they fit congruity. The trouble with animations is they don't fit that apprehension principle. They're hard to perceive, okay? And I'll go more on this on Wednesday. They're too complicated, too much is going on at the same time. You can't follow it. But Julie Morrison's doctorate was just one ball going on a route. And even in that case, the animated graphics weren't better than the static. So I think a deeper reason why animations don't work any better than static, sometimes they're even worse, rarely, but sometimes, is that animations don't match our conceptions of processes that take place over time. So think about the route. The route is go left, go right, go straight, right? The route doesn't, if you had to do a route showing you, going across the United States, showing you all 3,000 or 4,000 miles, right, in real time, what you need to get from someplace in New York to someplace in California, I mean, that would be ridiculous, right? All you need to know is take the Highway 80 until you get to, right? So that even a route you give is a sequence of discrete steps. So why do you make somebody sit through a whole animation if all they're going to get out of it is this set of discrete steps? Show them the discrete steps, right? So in the static graphics, if they're done well, do that. They're one graphic for each step. The third reason why animations don't work for educational reasons is they don't explain. Seeing something from start to finish, like a flower grow from a seed, doesn't explain how it happens. People watch those things for millennia without understanding how they happen. Watching rainfall doesn't tell you how rain happens, right? You need to, and so doesn't provide, seeing something happen doesn't explain it. So those are reasons why I think the kinds of animations that are typical now don't work. Now you can make better animations that do all those things. And that's, I think, a challenge. Okay, so, one way of figuring out how to make a good animation would be to watch a good explanation. And a good explanation, so applying this research program, a good explanation zooms, changes angle, it uses analogies and metaphors, it compares it to other things. I mean, those are all the things that we do when we explain something well. So that all of those things could be brought into good animations, right? And that's a challenge. Yeah, question. So the question is, what if you make interactions interactive? In a way, interactivity is a whole different issue. It's not the animation, it's the interaction. So sometimes interactivity improves, sometimes it doesn't. And in fact, in many cases where children or school-age children, because many of these studies are done on children, although high school children are adults, college students, the animations aren't even used. People don't even use them. So people say, okay, animations are attractive, people will look at them more. In many cases, they're ignored. I mean, you know that yourself. When you open a box of furniture, you don't want to look at the instructions. You want to put the furniture together. Same with a computer, right? That's why the Macs are so good. You don't have to read the instructions. So interactivity is sometimes better, sometimes not. I mean, again, you know that from computer interfaces. Some of them have huge amounts of interactivity. You don't use it. It's too complicated. So, and some of the opportunities for interaction aren't what you want, right? Aren't what you need. They don't let you do what you really want to do, like zoom in or look at here or, get it in color or whatever. Okay. So we've also, as I said, more recently started looking at gestures. I haven't given you the punchline yet on the assembly diagrams, but I will. So we've also looked at gestures. Now, gestures can be animated. That's the example. That's the one advantage that they have over diagrams. Diagrams are static, so it's a challenge to show change over time. Arrows is one way of doing it, but the nice thing about gestures is that they can show action. They can enact. They can also show a point. They're a little worse at structure, because if I want to show you the structure of something, I have to rely on your memory. The TV card has two sides and a top and a support board and another panel, and now you have to remember that when I point at this virtual object in the sky. But gestures can enact, okay? And if you ask somebody instructions how to get somewhere, you better look at their gestures, because often their words are wrong. When Amos used to tell me when I was driving, the few times I was driving, and he'd tell me always, Tifnei Yamina, right? And he's pointing, the Tzankanaya. Okay. Anyway, He was terrible on left and right, and I knew just watch his hands. Don't forget what he said. Okay. So we had people make demonstration videos of how to put the TV cart together while they were putting it together using speech and gesture or gesture alone. They also had a narrative structure. Okay? So they had an introduction. They would usually wave. Okay? They would hold up the parts, the big parts. They would hold them up and exhibit them, the big parts there. They pointed to the small ones where the holes are that you have to put the screws in. They would point to them. So this is like a part menu. In fact, at the very beginning, they would give you a part menu, show you all the parts. Then they segmented the actions into steps. They did a step initiation. They'd often, hold up fingers for each one, and they'd give a step completion. They'd do something like this that said that it was done. Okay, they often gave step previews. So they would first preview the action they were going to do. This guy does it. I have a video, but I'm not going to show it now. That shows you what he's going to do, and then he does it. Okay? They made the actions visible. So they went to great extremes. They're putting this TV cart together in front of the video. It would be much easier if they did it facing themselves. So they're doing things like this. I mean, to make it visible to the camera, right? And this guy isn't, right? So he's blocking the view. Okay? On the whole, they made it visible. They make models with their hands, with gestures. So they model the structure just the way I did now, and then they show you the structure. They also model the action. He's modeling the action that you have to do, showing you where you do it and how you do it. So they're creating mental models of the structure, mental models of the action. I don't say that everybody who gestures does this. I'm taking the best cases. Okay? And they conclude. They present the thing to you. It's like the sparkly lines. They're done, and they present it to you. Okay? So it's got a narrative structure. So, again, elements of explanation are the parts. They can be drawn or named or pointed to in the case of gestures. They're the actions, and they can be done with arrows in the diagrams, with words like push, insert, lift in the words, and they're done with movements in the gestures. And then there's the perspective is also essential in the explanations, and again, it can be done by the diagrams or by the words or by the gestures, and it is done. Okay, the structure again is a beginning, an introduction, a middle, step by step, an end, and an accomplishment. You've succeeded. And all three kinds of explanations have that. The design principles that we implemented, again, are step-by-step action and perspective. And here's our final test. On the left are the instructions that came from the factory. Okay? They're not terrible. They're not as bad as some of the ones I've shown you. On the other hand, it's an easier object. They are just a blow-up, right, of the parts without a step-by-step. These are ours. So we did a test, and this we did holding our breath, because any of you who've done educational or HCI work know that when you go and do the experiments, you often don't get differences. You know one kind of instructions is better than the other, but because students are smart and can learn from everything, and you've given all the information in both A and B, sometimes you don't get differences. So we held our breath. We gave them the factory, the computer generated. We also gave them the very best hand-drawn ones that we've gotten from a high spatial subject, and we won. Okay? So this is time to assemble. How much time you can see with a hand-drawn, it's almost 19 minutes. With a factory, 16 minutes. With ours, 10 minutes. And those differences are very significant. As far as errors go, we weren't any better than the factory ones. They made half an error with ours and a little more than half an error with the factory. They made more 1.5 errors with the hand-drawn on average. But we weren't that much better. But given that we cut the time by a third, we won. Okay? So, and we also won in the ratings. We had people rating how easy was the task. And the people who did our instructions said it was a piece of cake, snap. And the people that used the other said it was hard. Okay? By the way, for this study, we took only low spatial students. Okay? The high spatials wouldn't have even looked at the instructions. They just would have put it together. So we took only low spatial. Okay. So, designing effective diagrams. We've shown that you can reveal the mental models from descriptions and depictions, also from gestures. We've induced and tested. We've shown you ways that we can induce the cognitive design principles from student-produced designs. Okay, we're using students to produce them. We're creating this process in the laboratory where people produce and people comprehend, and people produce and people comprehend, and things get better. So we've induced and tested cognitive design principles that instill the mental model on others, and we've shown how to instantiate the design principles in a design or in an algorithm. And I'll end the way our subjects ended, by giving you their TV card. So thank you very much, and I'm open to your questions.